Alex Floor here doing the extra credit physics video for Lab MO5 on the second physics lecture that was held on Monday, April 8th, featuring Martin Buchwald. His lecture was What Happens Before the Big Bang. Basically, this lecture talked about the standard model of cosmology. Suggests that the universe started with a phase of very high density described by general relativity and a singularity. Quantum gravity attempted to resolve the singularity by a more fundamental microscopic theory whose equations remain valid and could tell us what happened at or even before the Big Bang. This talk basically reviewed one approach, loop quantum gravity, and discussed several surprising new results that shed light on the structure of quantum space-time with implications for mathematical modeling and conceptual questions in cosmology. But before that, it would make a lot more sense to talk about what actually happened before the Big Bang. Boom. That's Martin Buchwald. So what did happen before the Big Bang? It happened about approximately 14 billion years ago, and during that time, our universe and all the matter and energy and everything was condensed into a very small space. It had a high density with lots of energy and was extremely hot. And almost in an instant, there was a sudden explosion, and it went from being really small, smaller than even an atom, to bigger than a galaxy, and just kept expanding, and in fact keeps expanding. And during that explosion, there was matter and antimatter formed, and first it was just that, and then as the universe began to cool down, there started to form electrons, protons, and neutrons, and as the universe started to cool down even more, more atoms and elements started to form, and the universe as we know it is here now, and it is still expanding. So now we go back to what the lecture actually talked about, and it is, what is quantum gravity? And as we can see right now, as I learned from the lecture, there was a lot to the lecture, by the way, but one of the parts that got out was quantum gravity. And so to give a more broad definition, I researched it on Wikipedia, and what I found is that it is a field of theoretical physics that seeks to unify quantum mechanics, which describes 3 of the 4 known fundamental interactions, with general relativity, which describes the 4th fundamental interaction, gravity. So from what we know, the fundamental interactions are electromagnetism, strong nuclear interactions, weak nuclear interactions, and gravitational reactions. And we want to figure out how they all interact together, and it's important that what quantum gravity does is it explains and unifies all interactions, and it's able to predict the outcomes of situations where both quantum effects and strong field gravity. So then going further into what he actually talked about, and he used mathematical models and different pictures, and he actually assigned some of his own names to different states of energy, such as the Hell state, was the loop quantum gravity. And that's also, I also found a definition of that to make it a little easier to understand, which is that loop quantum gravity is a theory that attempts to describe the quantum properties of gravity. It is also a theory of quantum space and quantum time because, as discovered with general relativity, the geometry of space-time is a manifestation of gravity. So there's all these different things. I know that's a lot to comprehend right now, but I'm going to try to break it down a little bit more. So to break it down even further, I'm going to share what I learned on a more holistic level. And basically there was a lot of new math terms and way to interpret them that were made sense. There was all sorts of gradients taken and integrals and all these graphs that described how space and time interacted. But even more specifically, he talked about space relativity. And you can break space relativity up into special relativity, and general relativity. Now, special relativity is basically space and time. Basically says that space and time are not absolute. It's in 4 dimensions, and to put it in account for something that we understand and we learned in Physics 2211, is it accounts for the speed of light, which we know is the universal speed limit. You can't find anything in the universe that, or we haven't so far found anything in the universe that is above that speed limit, because as we approach the speed limit, or the speed of light, which is 3 times 10 to the 8th, yeah, it takes huge amounts of energy to even just jump up to the little just to increase your energy. And then we talked about general relativity, which says that space and time are dynamic and expand to influence and are influenced. So that instead of them being absolute, they have influences on each other and have other effects. So, and this also accounts for things such as gravitational time dilation, gravitational lensing, gravitational redshift of light, and gravitational time delay. And another thing that he put into perspective is that space and time coordinates are different to the relativity or frame of reference. And from what I understand from the lecture, that can be described in the picture on the bottom left-hand corner. So now, what did I already recognize? And surprisingly, when I went there, I started looking at some of the math and thinking like, oh, I got this. Like, I can see what's going on, and I recognize a lot of the formulas from Calc 1, 2, and 3, such as gradients, integrals, and functions, and different ways to graph and the planes that they were put on. Another thing that I also referenced from chemistry, or from physics, that we also learned was frame of reference, how depending where you view the system or how you view it tells you a lot about what you learn about the system. And of course there was a lot of different energy or different laws, physics laws, that I started to recognize, such as Newton's law, Einstein's equation for special relativity, and energy principle. So there were things that really sparked my curiosity, which I wasn't quite sure of that when he was talking. I understood such things as ladder operators, and there's also a thing called state of hell, which was really interesting, and it was how what the emptiest space is, and the Bourgeois who gave the talk actually was one to coin that term, and it's a special term he uses to describe the empty spaces on different energy levels in before Big Bang and afterwards. And this also goes back to, this becomes all relevant on the history of, physics and discovering all the information that we know now, was the viewing of the first atom from 1950. That happened in 1955 by Erwin Mueller. And I went and actually researched that because it was really interesting learning about the different technologies and how those had evolved at that point, which allowed us to view the first atom. And I thought it was incredible that only, it was only a few years ago, if you look at it in the relativity of what we've learned through physics, that all these great advances have been made. Moving on, we also learned about quantum corrections to apply to all bodies, and there's different ways to calculate the quantum energy for certain matter, but there's a broad way to apply it so that it applies to all bodies. And then we also learned that wave functions, it's been learned that wave functions can be expanded to a time before the Big Bang, which really starts to give us a time period to understand when these things were happening, how they happened, and why they happened. So after that, I wanted to learn more about what he was talking about, because honestly I was a little confused and really wanted to understand what was going on. And I had previously read a book called The Quantum Zoo by Marcus Chowan, which what I was told it would do is explain all these complex physics terms in a way that really almost anyone can understand, and it's called A Tourist Guide to the Never-Ending Universe. And it really would just present you with all these interesting facts, like, 1% of static on TV tuned between the stations is a relic of the Big Bang, or, I don't know, that, the faster you go, the slimmer you get, which, hey ladies, it's pretty cool. But so I went back, and after reading this, I started to review the chapters and started to understand the book like I hadn't before, and there were new topics that made sense. And I think as I continue to learn more about physics and learn more, through the years, that I'll start to do this again. But overall, very interesting lecture.